type of model. So in the case in which we just regress our dependent binary variable, this denied variable, so whether the mortgage was actually accepted or not by the bank officer, depends on the payment to income ratio. We just use the standard techniques that we know of, these OLS estimates. And how do we do that? By using this common. And by doing that, then the question is how to interpret these coefficients. We learned that when we estimate a regression line with this type of model, this is the type of population regression model that we are gonna estimate, and then the predicted y that we estimate in this case, so the conditional mean of y given x, now has a particular interpretation. This is the probability that y is equal to 1 given x. So this is the probability that the application for the mortgage will be actually denied given x. So when the payment to income ratio is equal to 0.4, what does it mean? That the predicted value of y is equal to 0.5. This means that the probability that the loan will be, that the application for the mortgage will be denied is 0.5. So this is the interpretation that we are going to assign to the predicted y, so to the regression, population regression line, and also then as a consequence the effect of a 1 unit change of x on y is the effect of increasing x by 1 on the probability that the application for the mortgage will be denied. Okay, so this is the difference with the probability that y is equal to 1 when x increases by 1. So this is the interpretation that we assign, and given this estimation, then we mean basically estimating a coefficient equal to 0.6. We are saying that by increasing the payment to income ratio by 1 unit, the probability that the application for the mortgage will be denied increases by 0.6. So this is what we, how do we interpret these coefficients estimates? But then, so whether we increase the probability, whether we increase x from 0.3 to 0.4 or from 0.1 to 0.2, the effect on y will be the same. Okay, so the effect on y will be, since this is a linear model, will be 0.6. So if we, so this means that if we compare the predicted probability of y equal to 1 when x is equal to 0.3 and when x is equal to 0.4, we have beta 1. Okay, this is what we always did. Beta 1 is the difference in the predicted y when x increases by 1 unit. Okay. So delta y over delta x is equal to beta 1. Okay. And when we estimate beta 1, this is the difference in the predicted value of y. So here we just have that instead of having y, we have the difference on the probability that y is equal to 1. And this is the predicted probability when delta x is equal to increases by 1. And this is beta 1 in our linear probability model. Okay, so the interpretation is the difference in the predicted probability when x increases by 1. So we just applied what we know of, and this is the case of the linear probability model. So which are the advantages? This is very simple. We can actually apply the tools that we know. We estimate this model by OLS. We make inference as we are used to which had disadvantages that for probabilities to estimate probabilities that y is equal to 1 or equal to 0, it's better to use something which is non-linear, so a non-linear probability model, because we want that the effect of a change in x on y is not equal over x, but it is lower for extreme values of x. Okay, so we want that for this is something that I already said, but when the payment to income ratio is very high, by increasing this payment to income ratio, the effect of being denied is very small because it's too high. So the payment to income ratio is too high, and the effect of increase, the marginal effect of increasing the payment to income ratio should be lower. And the same for when the payment to income ratio is very low. So when actually we have people which can afford to pay the loan because they have a high income, then whether this payment to income ratio is 0.2 or 0.21 doesn't really make a big difference in terms of whether they will be accepted or not. So we want something which here there is a higher effect of increasing x on the probability of being accepted, and for extreme values of x we have lower effects. Okay, and this is the nonlinear model because we want that beta 1 basically is different over x. It's not anymore constant, but it's different for over x. So it's lower for extreme values of x and higher for intermediate levels of x. And this ensures that the probability of being denied is constrained between 0 and 1. Okay, so the fact that we are actually using a nonlinear probability model ensures something that has to be applied for probabilities. The probability has to be defined on between 0 and 1. So that's why we need to use nonlinear probability models. And this is the case of the probit and the logic regressions. So these are two models which use a nonlinear functional form of the regressors, of the parameters. And how do they differ? They differ by the type of functional form that they use. Okay, so in the case of in this case, so for nonlinear probability models, we have that the probability that y is equal to 1 is not anymore equal to beta 0 plus beta 1 x in the case in which we have just one regressor, but it is a nonlinear function g of our regression, standard linear regression, okay, in k regressor. So this is the extension to the integral regression models. So this is a nonlinear function of the parameters, as you can see. So while before, if you remember when we talked about polynomials, logarithms, and interactions between variables, we were accounting for a type of nonlinearity in which we had the nonlinearity in the variables, but linearity over in the coefficients. Here we have a nonlinear model in the coefficients. Okay, and this complicates stuff very much, in the sense that while before we were able to write the model in a way that we could have used OLS, still the tools that we already know of, here we need other tools, because this is a nonlinear model in the coefficients. And these nonlinear functions are defined this time, and this is what we wanted, between 0 and 1. So how do they differ? Here we have in the probit model, we have that this nonlinear function of this equation of z, we define by z, this equation is equal to the cumulative density function of the standard normal distribution, and the cumulative density function is the probability that the variable, the random variable, is below a certain number. Okay, so this is how we define the community density function. So the probability that the variable is takes on values which are below a certain particular value, which is the small z. And in the logic case, we instead have a logistic probability distribution. Okay, so this is the community density function of a logistic distribution. So they basically use different non-linear functions. So this is the case of a product model. This is still again a scatter plot of x here. This is the payment income ratio. This is the dummy variable, which is defined on y is equal to 0 or y is equal to 1. And when we use a product model, then whether we increase the payment to income ratio from 0.3 to 0.4 has a particularly big effect, I would say, on the probability of being denied. But if I increase the payment to income ratio from 0.2 to 0.3, as you can see, the probability of being denied increases by a smaller amount. And the same for big payment to income ratio if we start it here. So it depends on the initial value of x. The effect of increasing x on y depends on the initial value of x. So whether we increase starting in 0.2, in 0.4, or in 0.6. And this is what we actually wanted. And we do this by a profit model, and you will see that actually there are no big differences when we use a logistic function. So in this case, we model this nonlinearity by using, as I said, a standard normal distribution. And then we can write that the probability that y is equal to 1, instead of being beta 0 plus beta 1x, is the community density function at this specific 1z is equal to this value. And this is a value that we can estimate. Okay? But still, so we can estimate beta 0, beta 1, but still the effect on the probability of being denied depends on x. And this is what we want. It's not constant, but it depends on the initial value of x, whether the effect of increasing x by 1 on y. And we will see this. So basically, let's assume that we estimate beta 0 equal to minus 2. So this is the intercept of our population model. Then this is beta 1. So we estimate a positive effect of x on y, and also we have that the payment to income ratio is equal to 0.4. Okay. Given these two estimates and the value of x, we can compute the predicted probability that y is equal to 1. So the predicted probability of being denied. We just replace in our linear equation, linear model, beta 0, beta 1, and x, and then we compute the community density function using the standard normal distribution at this specific value, which is equal to minus 0.8. So this is basically the probability that this random variable z is below minus 0.8. And also, visually, basically, we are computing, given this standard normal distribution, this is z, okay? This is the standard normal distribution distributed centered in 0 with the variance equal to 1. Then, of course, here we are in the case in which z is equal to minus 0.8. We take the tables of the standard normal distribution, and we have the probability that z is below minus 0.8 is actually the 21%, is equal to 21%. So this is actually, this complicates just a little bit the interpretation of the estimates of the linear probability model, but still is something that we can do. Okay, we have the tables for the standard normal distribution, and it's easy to be interpreted. So basically, in Stata, what do? We just, instead of using regress and then the dependent variable and then the regress and then the robust, the statistically robust standard error, so we use this command, which basically calls the type of model, non-linear model that we are using. So we write down the profit, the knife, and then the regression, and how we compute the standard errors. And as you can see, so here we are not estimating by OLS because we are on a linear model in the coefficients, and this for this to actually use this type of methods, we are using the what is called the maximum likelihood estimators.
But what is given like interaction 1, 2, 3?
So that is the iteration. So basically, it should start a search for the highest value of the likelihood, or actually, said in a different way, start a search for the best estimates of beta 0 and beta 1, which maximizes the likelihood. So while before with the OLS, if you remember, we were minimized, so we were actually searching for the values of beta 0 and beta 1, which minimized the sum of the squared mistakes, squared errors, so the difference between the observations and what we predicted. So we were minimizing the sum of yi minus beta 0 plus beta 1 x, in the case, of course, of just one regressors. And here we add beta 0 estimated and beta 1 estimated. Okay, so beta 0 and beta 1, the estimates for beta 0 and beta 1 were the solution of this minimization problem. Okay, so we took the derivatives of this with respect to beta 0 and beta 1. We actually put this equal to 0, so the derivatives equal to 0, and then we got beta 0 and beta 1. This is how we estimate coefficients by OLS methods. Here we are instead finding beta 0 and beta 1 by maximizing the log likelihood. So this is a different method, but we are going to see this in later on, just in 10 minutes, I guess. So this is the iteration. So it's searching for the highest log likelihood value, and it stops here, and this is the log likelihood, so the value of the log likelihood at this specific estimate. So this is the best, the highest log likelihood, and these are the best value which maximize the log likelihood. And then, if you can see, we are using a different statistic. So this is called Z statistic, and we are using the chi-square instead of the F statistic for the joint hypothesis testing. And we are also using another measure of fit, which is called the pseudo R-square, not anymore the R-square or the adjusted R-square for the case of multiple regression models, but we are using these different elements. Okay, and then the question is, still we have this data output. How do we interpret these coefficients? So if you remember, we are using the same variables, okay, as for the linear probability model, but before we had something like 0.6, now we have 2.9. So how do we interpret this coefficient? So we cannot anymore interpret this coefficient as the effect of one unit change of x on the probability that y is equal to 1, because now we have this additional function here that we need to take into account. So we just compare the predicted dependent variable, okay, when x is equal to 0.3 and when x is equal to 0.4. So it depends on, this time it depends on where you start with x. So whether you start at 0.3, at 0.2, or at 0.1. So I would probably ask you, so please estimate the effect of increasing x on the probability for the loan, for the mortgage application to be denied when X is equal to a certain number. Otherwise, it doesn't really, my question doesn't make sense. Okay, so it depends on the value of X. So where I start the change of X. So how do I do that? Basically, this model can be written in this way. So this is the probability that Y is equal to 1 given X. So the probability of being denied given the payment to income ratio of that specific entity. And this is the standard normal cumulative density function. So this is phi, and then here we have beta 0 plus beta 1 X. Okay, so these are the numbers that we estimated. So these are actually these numbers. So we have these estimates. We need to know from me at which value of X we are starting this to evaluate the change in X, and then we are able to compute the predicted probability of being denied. So this is what we are doing. So Stata delivers beta 0 and beta 1, but it doesn't deliver the predict the effect of changing X on the probability of being denied. This is something that we need to compute by using that table.
We cannot add this to the command, like we put the command and we put the exact payment ratio.
It depends also on the evaluation of the cumulative density function at the specific value that you compute for when X is equal to some
Yeah, but I
specific.
mean the calculation should be done manually. You cannot do it with SCADA.
You can do with SCADA. Everything can be done with SCADA. I will show that to you. So this is what we estimated. So if we have those estimates, the only thing that we can say on impact is that we have a relationship between the payment to income ratio to the probability of being denied, and this positive estimate is statistically significant. So this is the only thing that we can do without computing anything. So the only thing that we can infer from our result without computing anything. Then the interpretation of actually beta 1, so the effect of changing X on the probability of being denied, should be computed by comparing the predicted probability of Y equal to 1 when X is equal to certain value to the probability, the predicted probability of Y equal to 1 when we make the change. So after the change, prior to the change, if you remember, we've done this many times. So this is how we interpret coefficients, before the change and after the change. And this is the cumulative density function of a standard normal distribution evaluated at X equal to 0.3, given the estimates that we have from Stata. And then we take the tables and we compute the value of phi at Z equal to minus 1.3, and this is equal to 0.097. And then we do the same for X equal to 0.4, and then we just compare these two probabilities, and we can say that the predicted change in the probability of being denied when X goes from 0.3 to 0.4 is equal to the difference between this number and this number. So after the change, so the predicted probability of being denied after the change in X, and the predicted probability of being denied before the change. So the difference between 0.15, 16, and 0.09. Okay. And this is equal to 0.06. So why did I write also these two terms? Because I wanted you to see that this change in the predicted probability of being denied basically is is equal to the interval between. So if you want to, let me find. Allora.
Excuse me, Prof, the payment income ratio is the ratio between what and what exactly?
So the payment for the loan and your income. Okay, so it's a measure of how much you can actually afford to pay the loan with your money.
10,000 euros, so it's 10,000 and then divided on my income.
Yes. Okay, so it depends on how much you earn, whether you are able to pay your loan. Okay, so the bank evaluates how much you can actually afford to pay the loan by using your.
So basically, based on that ratio, they will accept or deny, right?
What?
Based on this ratio, they will accept or deny the request.
Well, we are using this variable as a good relevant variable to explain whether they will be denied or not, but there could be also other variables which explain this probability. But we are assuming that this is a good variable to predict whether the loan, the mortgage application is accepted or not. Okay, so we have said that by evaluating the predicted probability of being denied, given X, we will basically, with the profit model, we are computing the area, okay, underlying the standard normal distribution at some specific value for Z, which is equal to beta 0 plus beta 1 X. Okay, let's assume that X is equal to 0.3, if I remember correctly, then this value for z, which is equal to beta 0 plus beta 1 times 0.3 is equal to minus 0. Actually, let me use the numbers that we have here. Okay, so when we are at x equal to 0.3, given beta 0 equal to minus 2.2 and beta 1 equal to 2.97, then we have that the small zeta is equal to 0.097. And then this area here is the probability of being denied when x is equal to 0.3. Okay. Then, to assess to actually being able to interpret the effect of increasing the payment to income ratio on the probability of being denied, we need to, as I said, being able to compute also the predicted value of the probability of being denied when x is equal to 0.4. And this is what we did, and this predicted probability, which is the probability of being underlying, so it is basically the area underlying this standard normal distribution at z equal to minus 1. This is I don't know. This is when if x is equal to 0.3, then the small z is equal to minus 0.3, minus 1.3. And then the area underlying this distribution is this one. So this is the probability that z is below 1 minus 3. And so the probability of being denied equal to 1 when x is equal to 0.3. Okay. Then we need to compare this area to the area that we would have when x is equal to 0.4. Now when x is equal to 0.4, then z is equal to minus 1. Minus 1. And then the predicted probability is instead given by this area here. Okay, so this is the probability that z is below minus 1. Okay. Then to evaluate the change in x going from 0.3 to 0.4 in terms of predicted probability of being denied, we just need to compare the blue area with the red area. So after the change, before the change. So the red area minus the blue area. And the red area is the cumulative density function evaluated at z equal to minus 1 minus the blue area, which is the cumulative density function of the standard normal distribution evaluated at minus 1.3. So basically what we are computing through this difference is the black area here. So the difference between the red and the one area. So we are computing this difference. And this difference measures the change in the predicted probability of being denied when the payment to income ratio is equal to, goes from 0.3 to 0.4. So, and this is also, this makes sense also by intuition, because when I need to pay more with in terms relative to my income, the probability that I'm able to actually to pay the loan is lower, and then the bank evaluates this as a bad sign, and then the probability of being denied is higher. So the probability of this variable equal to 1 is actually higher, and that's why it increases by 0.06. Okay, this is how we interpret the coefficients. So how we use the estimated beta 0 and beta 1 to estimate the effect of a 1 unit change in x when x starts by 0.3 on the probability of being denied. Of course, if I start by 0.1, the effect is different. How is that? So in which direction does it go? As I told you, when x, I wanted a model which was nonlinear, in a sense that when the payment income ratio was very low or very high, the effect would have been lower. Okay, I wanted this kind of model instead for the payment for x at evaluated intermediate values. So when we were at x equals to 0.3, we had basically, we were here. Now we are evaluating at x equal to 0.2 or 0.1, I don't remember anymore. But the other example is when x is very low, the effect of changing x on the probability of being denied should be lower. Okay, by intuition. So for sure it's different, but should be lower. And actually this is something that we can prove just by, again, computing the difference in the probability, predicted probability of being denied when x is equal to 0.1 before the change, to the predicted probability when x is equal to 0.2. So still by using the estimated beta 0 and estimated beta 1, here instead of using 0.3, we have 0.1. Here instead of using 0.4, we have 0.2. We would have two different values here, okay, for the cumulative density function at these specific values, and then we basically would get an area which is which measures the difference between areas, which is smaller than this one. Okay, this is why we have an effect on the probability of being denied, which is equal to 0.05 instead of 0.06. So it differs with respect whether we are at x equal to 0.1, x equal to 0.3, and we would be able to prove that it differs also when x is equal to different values. Okay.
So the changes like from 0.1 to 0.2, this means the changes in the ratio. So this means we are either changing the loan amount or we are changing the salary amount.
This means that we are changing the ratio. So whether it's the numerator or the denominator, it doesn't really make a difference for the bank officer to be, for them it doesn't really make a difference. Of course, we are assuming that that ratio is a relevant indicator, is a relevant signal for the ability of the applicants to repay the debt. Okay, so whether the income is high and the payment is low or the other way around doesn't really change how the bank officer evaluates this. Okay, so now we so actually just to answer to your question before, how we could have done that computation with STADA, this is something that we actually already know how to do. Whenever we have an estimated value, we can call this, we can write this estimated value with this underscore b and then the regress. and this is beta 0, this is beta 1. Okay, so we just generate a scalar because this would be a scalar, no? 0. The predicted probability of being denied when x is equal to a certain value is a scalar, so we generate with stata a scalar which we call as we want, and this would be beta 0 plus beta 1 times 0.3. Okay, in the case that we had before. So this is another regression, but in the case that we had before, we just would write down this, and then we generate another scalar which is beta 0 plus beta 1 times 0.4. Okay, and then we actually tell stata to evaluate, to display this as the predicted probability of the payment to income ratio equal to 0.4, and to evaluate the normal is the cumulative density function at this value for that. So this would be that one in the case we had before would be equal to minus 0.3. So this would be norm prop of minus 1.3. Okay, and then we would do the same for x equal to 0.4. The difference is the effect in the predicted probability of being denied when x goes from 0.3 to 0.4. In this case, we are basically extending this model to the multiple regression model, and then we have also another variable here which may affect whether the loan is denied or not, and this is the race of individual. And then the question could be, does the race matter in terms of the probability of being denied? Okay, how do we do that? Again, we compute the predicted probability of being denied when x is equal to a certain value, and this other variable is equal to 0. So when we have a white person, with respect to the case in which this other variable black is equal to 1, which is the case in which we have a black person. And by comparing these predicted probabilities, we can assess what is the effect of increase of being black or white. So this is a discrete variable on x. Okay, so this is a dummy value, this is a continuous value. So the effect of being black or white on the probability of being denied given a certain value of x. So we need to fix x because we are not evaluating whether by increasing x we are changing the probability. We are evaluating now whether being black or white makes really a change. When x, we need to fix x because x, the value of x, since this is a nonlinear model, is important. So that's what we do here. So we estimated the model. So these are the estimates that we had from stata. We need to evaluate the area underlying z at this value. Okay, and this value imposes that we need to fix a value for the payment to income ratio, and we need to evaluate whether black is equal to 1 or 0. Okay, so this is the case we are evaluating at x is equal to 0.3, so at the payment to income ratio equal to 0.3, and then we compare the predicted probability when race is equal to 1 and race is equal to 0. This is something that these are numbers, we can compute these numbers, these are numbers again, and then we take the tables and we find that the area underlying these the normal distribution at one specific value for z is equal to 0.23 and 0.07 for the case of black person or white person. Then the difference is equal to 15.8. Okay, 8%.
So this means being black is getting more denied.
Yes. Yes. These are the estimates for using those data in 1990. Okay, in Boston. 2,380 observations in 1990 in Boston.
So, but the interpretation, we will interpret like being white and being black, or we interpret only the difference?
The difference. So actually, we interpret as it depends on what you are interested in. Okay, you can be interested in what is, so your question, it depends on your question. What is the effect on, your question could be, what is the probability of being denied when I apply for a mortgage when I am a white woman? I could also, for example, add another variable in that model where whether I am woman or man.
Oh, so
And then
the 15%, so I will say black people will be denied at 15%.
No. So here we say that a black person is with a payment to income ratio equal to 0.3 will be denied with a probability equal to 23%.
Okay.
A white person with a payment to income ratio equal to 0.3 will be denied at this specific 7.5%.
Okay.
Then what is the difference between that? So for women, what is the effect of being black on the probability of being denied? By being black, the probability of being denied increases by 15.8%. Okay. So this is the interpretation that we are evaluating. When the payment to income ratio is equal to 0.3. It would be interesting to, for example, do this same exercise when x is equal to 0.4. We would see that the effect is different. Okay. Other questions? So now we are going to introduce this logic regression, and again, the idea is exactly the same. The only difference is that instead of using the cumulative density function of a standard normal distribution, we use the logistic distribution, which has this specific form. Okay, so instead of having phi evaluated at beta 0 plus beta 1x, we have 1 over 1 plus e at minus beta 0 plus beta 1x. Okay, so this is the z that we can compute by our estimates from STADA. We just need to, instead of taking the tables from the standard normal distribution, just compute this value. So nothing really big here. So again, when beta 0 is equal to -2, beta 1 is equal to 3, x is equal to 0.4, we just compute z. Again, it's equal to -0.8. And here, instead of evaluating phi at -0.8, we just compute this formula. This is minus 0.8, so we have 0.8. We can write this also in terms of f of z to say that this is another nonlinear function with respect to the normal distribution. And again, this is just by using the interpretation through the logistic density function. This is the area below the density function at z equal to -0.8, and this equal to 0.31 in this case. Okay, so it's basically the same idea. We are just using another function. And how do we tell STADA that we want to run a logic model? We just, instead of profit, we just put logic there, same dependent variable, same regressor, and then how we want to compute the standard errors. Again, we are using maximum likelihood estimates. Again, we are using the p-square and the pseudo r-square. And again, we have some coefficients that we cannot directly interpret. We can just say that the payment to income ratio increases the probability of being denied, and this is considered significant, but nothing more. To interpret the coefficients, again, just compute the probability of being the predicted probability of being denied when the payment to income ratio is equal to a certain value. Of course, in this case, we are leaving this general, so it depends on x. Okay, we just replace beta 0 and beta 1 here. When x is equal to 0.4, this is the infographic. When x is equal to 0.4, this is a number. When x is equal to 0.3, this is a number. We are computing directly the difference between the predicted probability of being denied when x is equal to 0.4 and the predicted probability of being denied when x is equal to 0.3. And this is the difference. So by increasing the payment to income ratio from 0.3 to 0.4, the effect on the predicted probability of being denied is the 6%. So the probability of being denied increases by 6.3 percentage points. So this is the interpretation that we assign. And actually, this is from this is a mistake. So when this goes from 0.1 to 0.2, I just wanted to show you that this effect changed whether x was going from 0.3 to 0.4 or from 0.1 to 0.2. And this also in this case we have a lower value there. Okay, so it's not really changing much. And again, for the black case in which we introduce another variable, we just compute the predicted value of the probability by using the exponential function here. So the logistic function f beta 0 plus beta 1 times the x equal to 0.3 when we have a white person, and we do the same when x is equal to, again, so this has to be fixed when we have a black person, and then the difference in these two numbers is 14.8%. So being black when x is equal to 0.3 increases the probability of being denied by 14.8%. These seem actually, all these seem to be very similar. The only difference is that we, in this, if you remember the scatter plot between with the x and y here, this is the logistic function, this is the normal function for a general database, and for the database that we actually used, as you can see, the probit model and the logic model estimate the same regression model. So this is the predicted y given x, no? As for the linear model, we had the line was what we actually estimated. So what we predicted, this is what we predict for each x, and the probit model, given our data, delivers almost the same, I would say, the same function as the logic model. And this was also seen by evaluating these effects by change before and after the change. And this is just a table, because whenever you want to compare models, you just basically put here, and you will see also the tables in the application section that you have in each chapter. There is this way to actually present your results through tables, where I introduce or do not, or I do not introduce a specific regress, so whether I introduce the interaction term or not, the logarithm or not. And this is what actually your book does pretty well. And this is also what we are doing now. We are comparing the three models that we have seen by using the constant, the payment income ratio, which is our variable of interest and controlling by the other variables, so the race of individuals. And while here we were actually able to interpret the effect on the probability of being denied directly, here we cannot do that, and we need to make that additional computation. But here also reported the directly the difference in the predicted probability when the payment to income ratio is equal to 0.3 between black and white applicants, and the differences, as you can see, are not very different between the product and the logic model. So there are no big differences normally in terms of results, but the logic model is computationally faster, and that's why normally we would prefer to use that. But given the new computers, actually this difference is not anymore so relevant. So we can actually use both without having our results change so much. Okay, so I just want to now devote 15 minutes to the estimation methods. So as I told you, we are not anymore using the OLS because we have no linearity in the unknown coefficients, and there are two possibilities. The first one is to use the nonlinear least square estimation, which extends the idea of the OLS that we used up to now to enter nonlinearity in coefficients. So that's why here we have the predicted, as I showed you before. This is we are minimizing this, we are finding beta 0 and beta 1 estimated, which minimize the sum of the squared differences between observations and predicted values. And while before we had, sorry, this should be better, no? Beta 0 plus beta 1x. Now with the profit model we have this phi, no? This is what we estimate as the predicted probability. So this is the only difference that we see here. So this is an extension. So we are doing the same. We are minimizing the errors that we make by estimating this model with respect to the observations. So this delivers consistent estimators, normally distributed estimators for large n, of course. Okay, consistency and asymptotic normality. Asymptotic normality are properties which are valid when n is very large, but this is not the most efficient estimator for causal inference. So there are other estimators which deliver lower variances for the estimates. So that's why we can say that this the nonlinear least square estimation is inefficient, because there is another estimator which is the maximum likelihood estimator, which is the most efficient estimator for the case of nonlinear probability models. So as I told you, here we were minimizing these errors. Now we are maximizing something, and this something is the joint probability distribution of the data. So what is the joint probability distribution? We have already seen that in our review of probability. So this is the probability of observing our data. And even so, if we have a model with some regressors, this is the conditional density of our data. Why? Given the regressors, and these densities are this joint density function, which when y depends on x is a conditional density function, is a function of the unknown parameters beta 0 and beta 1. Okay, and then our aim is to estimate beta 0 and beta 1, maximizing this joint density function of y, of all the y's, of all our data with n being the number of entities that we have. Okay, so we are maximizing the probability of observing our data given the regressors. In other terms, the maximum likelihood estimator, so beta 0 and beta 1 estimated, are the values of these parameters which most likely generated our data in population. Okay. And these deliver estimators which are consistent, normally distributed as the case of the nonlinear least square, but are also efficient. So they deliver the smallest variance of all consistent estimators. And then how we can conclude this. So this is something that I'm showing to you. It's not something that you need to, I'm not gonna ask you the formula here. I just want you to know what this means. So in the case in which we do not have a regressor, in the case in which our observations there for y1 up to yn, these are the probabilities. These are actually in this case these are binary variables equal to 1 or equal to 0 for all individuals. These are IID observations, so we don't have an X variable, a regressor on the right hand side. And these we are assuming that this Y variable is distributing according to Bernoulli random variable. And if you remember the Bernoulli distribution, basically Y would have been equal to 1 or 0 with the one probability P or 1 minus P. And then the mean of this Y variable, this Bernoulli variable, is equal to P. And then the only parameter of this distribution, which is unknown, is P. And then the question is, let's estimate P. We are not estimating beta 0 and beta 1 because we don't have X, okay? But this random variable depends on some parameter. Our aim is to estimate this parameter. And how do we do that? We want to estimate this parameter by maximizing the likelihood function. So the first step of this estimation procedure is to write down the likelihood function. Then once we write down the likelihood function, then we maximize the likelihood function, finding the estimates for P in this case. And this would be the maximum likelihood estimate. And in this case, what we have is that the probability we need to compute first. So the likelihood function, as I told you, is the joint density function of our data Y. Okay, so the joint density function, if it is depends on whether we have IID observations or not. In the case in which we have IID observation, the joint density function, which is the probability of observing jointly each observation, is equal to the product of individual density functions. So the probability of observing each observation, so the probability of y1 equal to y, this small y1 is the probability of observing the first observation. This is the probability of each observation has a probability distribution. You remember this, no? So each observation has a probability distribution. This individual probability distribution, if the observations are IID, if we multiply this individual probability distribution, we get the joint density function of all our observations. If the observations are independently and identically distributed. So given that the probability of each observation can be written in this way, because this is the probability that y is equal to 1 to y, and then the 1 minus the probability. So this is the probability of each observation. Then the joint probability function is the product of the single probabilities. Then for those who are interested, we can go, we can see the formula there, but this is the joint probability distribution written in another way of our data for y1 going to up to yn, and depends on p. Okay, then we take the log because it's easier to work with the logarithm of the likelihood, and this again depends on p. And then we maximize the log likelihood by setting this log likelihood equal to the derivative of the log likelihood equal to 0. This is what we did also with the OLS, and we find, so that is the derivative. We just made some formulas. I gave you this formula just because in your book this formula are not there. So for the ones who are interested, you have all the steps here. And then the estimated parameter which defines the probability distribution, the Bernoulli distribution, is equal to the mean of y. So basically we maximize, we first were able to write down the likelihood, so the joint probability distribution of our data. Then we take the derivative with respect to the unknown parameter. This we set this to equal to 0, and then we find the estimated parameter that we are searching for. Okay, so for the profit model, something changed here because we don't have any more IID observations. So we have a dependent variable and an X variable. Okay, let's assume that we are in the multiple regression model extension, and then the probability of each observation is not anymore P, if you remember for the Bernoulli distribution, but is given by the cumulative density function evaluated at these values here. Okay, this is what we have just seen. So while before we had that the probability of each observation was a number, now we have that the probability of each observation depends on X. And then we keep basically computing, then we actually compute the joint density function of each observation. And this is the joint density function of, the joint density function of all our data. And then we maximize the log, like we take the log and then we maximize with respect to beta 0 and beta 1. So we would have basically a set of first order conditions, or the derivatives with respect to beta 0, the derivative with respect to beta 1, the derivative with respect to beta 2. Those are all equal to 0, and then we find beta 0, beta 1, beta 2 estimated. Okay. We don't need to do this by hand, because this is something that Stata does for us. I just wanted you to know that there is something underlying. Okay, so those numbers do not come from nowhere, but there are computations that Stata is doing, not only because we are in the maximum likelihood estimation case, but also for the OLS it was the case. We are just maximizing another function. Before we were minimizing the sum of the squared residuals. Now we are maximizing the probability of observing our data. This is what is different here. Okay. And this is for the logic model. Again, the only difference is that now we are replacing this phi function with the logistic function. And then again, we would have, by using the maximum likelihood estimator, consistent, normally distributed, and efficient estimators. Then going to the measures of fit, I just want to you to know that instead of using the R-square or the R-square adjusted, we use two other measures, which and if you remember, Stata provides the second one. but the first one is the fraction correctly predicted. So this is how it is called, which is the fraction of observed wise. Okay, so the data for which the predicted probability is above 50% when y is equal to 1. So if the observation for the individual I is equal to 1, if the model predicts a probability that y is equal to 1 above 50%, so this means that this is a good model. Okay, because if in the data y is equal to 1 for that specific observation, and the model predicts that this probability is above, that y is equal to 1 is above 50%, then the model is doing a good job. It's a good sign. So the model is is a good model. So then the fraction of this fraction correctly predicted is the fraction of y's over our sample, for which when y is equal to 1, we are predicting the probability of y equal to 1 above 50%. Or is below 50% when in the data y is equal to 0. This is easy to understand because it's very easy. So basically the model is good in the case in which we are very close to the observation. If y is equal to 1, I'm predicting, so our model is saying that the probability that y is equal to 1 is high, so this is a good model. If y is equal to 0, then our model is predicting that the probability that y is equal to 1 is low. So this is something that we can understand very easily by intuition.
This is because we are using Bernoulli.
No. We are in the case in the standard case of probit and logic models. No, the Bernoulli was just basically a first case to understand how to compute the maximum likelihood. Okay. But here we are back to the case of a probit or logic model. We want a model which predicts that the probability of being denied for a particular individual is equal to 1, is very high when actually y is equal to 1. When that specific individual in the data is equal to 1, is denied. Okay? And predicts that the probability of being denied for that specific individual is low when in the data that specific individual is actually denied, is not denied, when actually y is equal to 0. So predicts a probability of being denied which is low for the observation for which the individual is instead accepted, for which y is equal to 0. So this is
but we're not analyzing like one individual in that data. We have like so many, so the starter is giving us as a group, not as a person.
true.
So how we can know that y is equal to 1 for all those 100 persons is higher than 50%?
So what do you mean? So actually we have in the data when yi is equal to 1 or not, right? In the data, this is something that we have.
Yeah, but I mean, we don't have it on one person. Like the data is for so many people.
True. Yes.
But you are explaining that only y is 1. This means for one person.
So you have your data for y for n entities. Okay. So you have actually the payment to income ratio of n entities, and you have whether these people have been denied or not. So this is what you have.
Yes. So this means we are saying like the n is equal to 1, and if it's higher than 50%, so we know that all these people they have been rejected.
Yes.
So like this is we see it in the like the two.
We are computing the fraction wise. Maybe I understood what you're saying. So basically, you're saying in the data we have n entities and we have this yi. This y which could be equal to 1, 0, 1, 0, etc. But we estimate one specific predicted probability on average. So this is what we estimate on average, no?
This one, where are you see it in the outcome of SATA? How I can.
So actually, in the outcome of STATA, this is not delivered because it's not interpreted as a good measure of it. But we can do that. But if I interpret correctly your question, you are saying that you estimate something on average, while in the data you have something entity by entity.
Yeah.
But then, and this is true, but then you need to compute the fraction of y's for which this average that you are estimating is a good proxy of your observations.
So anyway, this one is not delivered in the SATA.
No, because this is something that actually is just used to understand how we interpret the goodness of fit of such models. So we cannot use anymore the R-square. This is a possibility, but STATA doesn't deliver this type of measure of fit because it doesn't really reflect the quality of the prediction. So what does it mean? That if y is equal to 1, this observation, if yi is equal to 1, this observation is interpreted as correctly predicted, both in the case in which your predicted probability is very high, or in the case in which your predicted probability could be 60%, 61%, etc. So there is this threshold, so above or below 50% is good or not, and we don't really, in the end, this fraction correctly predicted is just a number, so we want something which actually is a good track of how good we are doing. Okay, so it doesn't really make a change, so whether the predicted probability is very high or just a little bit above the 50%. That's why we don't use that, but we use the pseudo R-square, which measures the improvement. So it basically, this is a measure which uses the likelihood function to assess whether by including X we are explaining more or less of Y. Okay, and in other terms, it measures the difference in the value of the log likelihood function, of the log likelihood function, when X is equal to 0 or when we have X in our regression model. Okay, and then in the case in which we have normally distributed errors, this pseudo R-square is actually equal to the R-square in the linear model. And then just to also go back to our sources of bias and inconsistency of our estimators. Again, also in this case, we have all the threats to internal and external validity that we have seen. So in terms of omitted variable bias, functional form that we are using, whether we are using a standard normal cumulative density function to recover this nonlinearity, so whether we are using a logistic distribution, whether there is a measurement error, sample selection bias. So all these sources that of bias, of endogeneity, if you remember, that we have done, that are actually applied to the linear models, apply also to the nonlinear models. So just to conclude here, so we are in the case in which y is, so the dependent variable is a dummy variable, we interpret the dependent variable as so actually the conditional mean of y given x, so the regression model that we are estimating as the probability of y equal to 1 given x. We have three models, the linear probability model, we didn't do anything different, but we have a constant effect of X and Y, and this doesn't really apply very well to probabilities. We have the probit and the logic models. These are nonlinear probability models which differ in the function of order that we are using to track this nonlinearity. And then to assess for these two cases whether what is the effect of delta X on delta Y on the difference in the predicted probabilities of Y equal to 1, we need to just compare the two predicted probabilities before and after the change. And given that we estimated the coefficients to do that through the maximum likelihood estimators, which delivers consistent normal distributed and efficient estimators for our models. Okay. So are there questions on this? Okay, good. Thanks.
Thank you, Ross.
And have a good weekend and see you Monday.